I'm calling this boat Gumption Trap because every step along the way in designing and building it and testing it was just one problem after another that made me want to lose motivation. Probably 80% of the time I spent building and testing this thing was just a constant stream of solving one unexpected problem after another. But that is just kind of the way it goes with these types of things, and you got to realize that that's just part of it, not just an obstacle in your way. Here's an overview of my self-driving solar-powered boat. It uses two pontoons made of 4-inch PVC pipe for flotation. The main solar panel is mounted on the frame, which is 2020 extrusion, attached with 3D printed brackets. It has the compass and the GPS antenna mounted externally to get the best signal and reduce the amount of interference as much as possible. This is a tow hook in case I need to pull it around, which I did. And in the rear, my two motors and propellers are mounted inside these shrouds. It steers with differential thrust, and these are mounted to the PVC pipes with these 3D printed brackets. I made those as several pieces so that I could disassemble it and replace this center part with a bigger one in case I wanted to adjust the height of the shrouds and propellers, but that proved not to be necessary at all, and in retrospect I would have gone back and reinforced that connection a lot more than it is, because it does introduce some drag being a flat surface that's mostly underwater, and it's fairly weak as well. And the underbelly, last but not least, is a waterproof box where all my electronics are installed. That never goes underneath the water surface, but it does get splashed quite a bit. It's designed so that when sitting in the water line is around halfway up the diameter of the PVC pipe. The frame is made of 2020 aluminum extrusions just bolted together with these right angle brackets in a few places, and the solar panel bolts onto it in the corners. Underneath is a waterproof box mounted to the frame with some 3D printed brackets that are epoxied to the side of it. These zip ties are a backup to hold onto it in case that fails. These connections go to the GPS antenna and the compass. I can open this to access all the electronics. That is where my SD card goes in, microcontroller, GPS module, receiver, ESC, of course my battery, and my solar charger. A little bit of a rat's nest, but that's okay. This is where I plug in the main power. I've left a few quick disconnectable connections in place so that I can swap parts easily if need be. All the lighter parts are held in with this Velcro tape that makes them easy to remove and reinstall. And the battery, being the only significantly heavy part in here, is zip tied down to these brackets which are adhered to the inside of the box. And that's just cyanoacrylate, but it held up really well. And I have some stripes of tape so that if I unplug this, I can easily tell which one came from where. All of the wiring enters the box through drilled holes that are sealed back up with hot glue to fill in the excess. And this is where the solar panel enters the electronics box. This tape is to prevent water from getting into some of the sensitive connections. Run through my code. So here's the libraries I'm using. For the GPS stuff, I initially establish an arbitrary set of coordinates just so that it can have something to point to for testing, but normally the coordinates are stored in this array, which it reads off of the GPS SD card. As far as the RC transmitter stuff goes, that's pretty simple. I have a lot of stuff using this progmem callout. That's to save memory, save dynamic memory. Indexing for the SD card, setting up some of the drive control stuff. These are acting as servos, even though they're really brushless DC motors using ESCs. That just basically outputs a range of PWM values acting as a throttle. This sets up the compass, These are the offsets that I got from a calibration I performed on them. That makes sure that it's accurate as it can possibly be. And for the setup, I'm checking if the SD is connected, checking if the compass is connected. This isn't really doing much right now, but I do plan to have this output different types of error codes and write it to the data logging, which isn't implemented yet, just so I can kind of troubleshoot stuff after it's already happened. The main loop is not much to it. This is all that actually happens. It reads the value of the switch on my transmitter, which sets auto or manual mode, and it either runs auto mode or manual mode. In auto mode, it initializes a connection with the GPS module. It gets the GPS data, latitude and longitude, and the reason I have it ending and starting is because the timing of the software serial connections seem to be kind of fighting against some of the other timing sensitive parts of my code, so that was kind of an easy solution to that. But anyway, it then gets the goal latitude and longitude out of that array I just mentioned, and it plots a course to that. Then it measures the compass data, and this logic I explained better on the physical model, but this is deciding basically how to throttle each motor based off of the compass heading relative to the goal heading. Let's see, it checks its distance to its goal waypoint, its goal coordinates, and if it's below 15 meters, that's close enough, it moves on to the next waypoint. And then manual mode is pretty simple. Basically just mapping the values received from the transmitter to motor throttle values. By the way, this variable mult is how I'm doing my throttle limiting. So normally 100% would output a value of 180 for the servo style connection, but I'm doing a 0.4 multiplier there to limit it to 40% throttle. And then this is a series of loops that reads all the data off of the SD card and populates my array of GPS coordinates. That's just for troubleshooting. It prints it out. And this smart delay function I stole from one of the examples in one of these libraries. That was actually kind of essential to making sure I always got good GPS data. It pauses the program while reading the GPS data. I called that up here. Here's some back of the napkin calculations for how I determined how much PVC pipe I need. So the mass of water displaced by the PVC pipe is this equation: density times volume, that's the density of water. Volume, I'm approximating it as a cylinder, ignoring the geometry of the end caps. Plugging in the diameter, or the radius of those cylinders, 2 inches, that works out to 10.2 kilograms of water displaced per meter of PVC pipe. Now I measured a sample of PVC pipe and determined its mass to be about 1.9 kilogram per meter. So its displaced mass of water minus its own mass gives it a net buoyancy of about 8.3 kilograms per meter. I also measured the mass of everything I'm gonna put in the boat except the pipes. That includes the battery, the motors, all that stuff, at around 4.7 kilograms. So I determined that I need at least 22 inches of PVC pipe to make that float. I did not include the term 9.8 for gravity because it canceled out, but I need 22 inches to make it float. I went with a safety factor of 2 plus a little more for a nice value of 48 inches, 4 feet. The reason I did that is so that if one pontoon completely floods, it'll still float because it has more than double what it needs. And that makes it nice and easy to predict the water line being exactly halfway up the side of the cylinders. Here's a CAD model of most of the boat that I did. I pretty much designed this around the solar panel with the electronics box underneath. I placed the 2 pontoons about as close together as they could be with a little bit of wiggle room. And knowing where the water line is based off my buoyancy calculations, I placed the shrouds just below the water line. and made their diameter about as big as it could reasonably be to enclose about the biggest propellers they could reasonably enclose. Now, I designed these mounts to be adjustable, and in retrospect I kind of wish I didn't do that. I did this because, especially with first iteration prototype type of builds like this, I do like to design in a whole lot of adjustability. I wasn't sure if I would need to raise or lower the propellers, so I wanted to give myself that flexibility without having to tear glue apart or reprint things. But in practice, they were fine right where they were, and I would have designed this to be a lot stronger. The reason I went with these shrouded propellers is because I anticipated a big failure mode being entanglement of seaweed or string or trash or whatever, and I'd hoped that this would help prevent that. I also designed my own propellers, mainly just for fun. I could have bought a cheap one, but the way I designed this was kind of like an airplane wing style cross section, and of course the pitch varies across its length. That is of course because the tips are spinning faster than the center, and that way the thrust is more even across the whole length of the propeller. I read a couple of articles about propeller design while I was diving into this, and oh man, that is a deep subject to get into. I'm certain this could be optimized for better efficiency, better power, and that's definitely something I would like to experiment with in the future, but this was perfectly sufficient to get me up and running. This is a test to make sure the software is reading my control input. I have a throttle, steering, and one switch. So that leftmost number is my throttle, which I can change with the left stick. Middle one is the steering, and the last one is just a boolean for the switch. This is a test of the ability to switch between manual mode, which shows the control input values, and automatic mode, which shows the sensor data values. This was actually kind of a nightmare to get working. So if it's in manual mode like so, and it loses signal from the transmitter, I can simulate that by just turning it off. It'll default back to auto mode. And these are not actual values, that's just placeholders.
Here's a test doing simultaneous readings of all the data it needs, including the latitude, longitude, and current heading. That'll change if I move the compass around. The latitude and longitude are staying the same because I'm not moving anywhere. And switching to manual mode, it measures the inputs from the transmitter. So everything seems to be working nicely. This test is for the motor output logic. On the screen are the left motor and the right motor values that the microcontroller is feeding their throttles, 180 being full chooch, 0 being idle, nothing. So with the steering stick, if I steer to the left motor will drop to 0 or close to it. And if I steer to the right, then the right motor will drop to 0 and the left stays at full throttle. And then changing the throttle stick will scale that accordingly. Okay, I'm super excited that I finally got this working, but this is a full system test of the power and the drive electronics. I'm just feeding 12 volts into the ESCs, which each have a DC-DC converter. One of them is plugged in right now, one of them is not, but the plus and minus from that 5 volts are feeding the entire breadboard circuit, as well as the Arduino microcontroller itself, which is not currently plugged into the computer at all, just running on its own. I put some tape on the motor so you can see they're spinning. At full throttle, we're drawing about 600 milliamps. Let's see if the steering is working. That's all the way left steering. And all the way right. That's incredible.
This is a test of my ability to read and write data off this micro SD card, which will be used to store GPS coordinates, and also just doing a quick paper layout of how I need to set everything up on my board. Just finished soldering everything into my prototyping board and giving it a test. That is such a relief to see that it still works after doing all that soldering. I've now got the automatic steering system ready and testing it. I've marked where my goal is, and it is actually calculating that based off a GPS measurement it took compared to the goal GPS coordinates on the SD card. And it's measuring its current heading from the magnetometer, comparing it to its goal heading based off some trigonometry. And if it's too far to the left of the goal heading, it'll reduce the throttle on the right motor. If it's too far to the right of the goal heading, it'll reduce the throttle on the left motor. So let's see it go. So if I'm pointed right at my heading, both motors will be at full throttle, and I've programmed in a little bit of a grace period of a few degrees where it'll keep them both at full throttle. But if I start to veer to the left, and you can tell the right motor totally cuts off at about 90 degrees. And if I go back the other way, left motor totally cuts off, and it's gradual. It throttles it accordingly. If I'm facing completely the wrong direction, if I hit the 180, it'll just switch over immediately. So it'll never be going backwards with both motors, hopefully. These propellers turned out all right. I printed them on the smallest nozzle I had on the lowest layer height I could. This is the leading face and the leading edge, which printed up, so that turned out nice and smooth, and I'm real happy with that. The only downside is there's some kind of roughness where the support was, and this is the trailing edge, which is a little rougher, but I'm willing to roll with this for now. I'm installing the propeller shroud and the propellers as parallel and straight relative to the pontoons of the boat as I possibly can to make it drive as straight as possible. If there ends up being a little more thrust or drag on one side, I can adjust the software to basically add a trim. I'm gonna turn on the jacuzzi to simulate some rough waters and see how she does. In order to verify the functionality of my power and charging system, I have my solar panel connected here, my 12-volt battery connected here, and just for a small load, I have a regular old DC motor I had laying around connected to the load. It draws only about 50 milliamps, which is much less than the entire assembly will draw while it's running, but really I just want to test that it's able to charge the battery and keep it charged while it's under a small load. I have that little DC motor underneath running, and the solar panel is in the sunlight, and really I'm just looking to see if the battery voltage goes up or not to verify that it's working. So after being outside and charging for about 20 minutes or so, the voltage went up about 0.3 volts. So I know it can charge the battery, I know it can discharge battery energy into the load, and I know it can charge the battery and run the load at the same time. All of the electronics are now mounted inside the waterproof box, either with Velcro tape or 3D printed mounts that are glued into place. The only thing that's free floating is the receiver, and I need to find a better way to secure that, but for now that's okay. And this is where I'll plug in the main power to turn everything on. I definitely over-engineered the enclosure for the magnetometer a little bit. It holds the PCB in tightly and uses a spacer to prevent it from moving vertically. O-ring gets bolted down to compress the O-ring. under a medium load, both motors. That easily goes to 2.5, 3 amps or so. And that felt like the range where the motors were about to stall out. So it seems that about 3, maybe 3.5 amps is probably about my max current draw. This is the underwater thrust test. And that's the problem I'm dealing with. The motors will spin for a second, then the ESCs beep, and they cut off. I've redesigned the propeller so that it takes less torque to rotate it by the motor at the same RPM. You'll notice the new one has a much less aggressive pitch and also a slightly smaller overall diameter. Otherwise, same concept. Dry test of the new propellers. So I just ended up solving that brownout problem by limiting the max throttle, and it seems to be running totally stable now. I limited it in the software, and so now it won't ever try to make the ESCs go so fast that they can't keep up. At 50% throttle, it seems pretty sustainable, running only off the battery right now. Obviously, I don't have the sun in my bathtub. And I can qualitatively feel a decent flow rate of the water, and I can feel some suction from the front. Even at 40% throttle, which is what it's currently limited to, I can feel quite a bit of thrust. Hopefully this will give you an idea. Feels like it's maybe 5 or so pounds when I push it back with my hand. All right, it's launch time. Water's fairly calm, pretty low wind, close to solar noon, although we are in the winter time. Brought a rescue vehicle just in case I need it. Let's make it happen. All right, I've paddled out to get a closer look. Seems like we may be having some type of navigation issue. It's kind of going in circles a little bit. So I've paddled out and I've retaken manual control, and seems like one of the motors died, sadly. Or maybe the ESC failed, but this motor's not spinning. I'll try to restart it and see if that helps. So I popped the hood. The good news is there's no water intrusion, but after restarting, still can't get that other motor to spin. So it seems like it's some type of hardware failure, either the motor itself, maybe the ESC, or potentially a connection issue. But at least I know it wasn't a navigation problem. This will be likely something easy to fix. And I've proven that it was able to go from all the way over where my truck is to its GPS coordinate over there, and then it started moving to the right to the next GPS coordinate somewhere over that way when it failed. So it's only a failure if you didn't learn or prove anything, which in this case I did. So I'm happy with that result, and I'll improve it for next time. I'm glad I took the time to make a tow hook, because that would have been awkward to paddle all the way back with it on my lap. This is what the file looks like that the SD card reader reads. The first digit is just representing the number of coordinate pairs. Then we go latitude, longitude, so on. Over here's what my first mission was supposed to look like. So this is where the public boat ramp is that I launched from. It went out to the middle of the lake, over to the right, make a U-turn, come back to the same point, and then go until you hit the shore. In practice, it made it out here, took a right, and it died somewhere in this vicinity. The whole mission would have been about 2/3 of a mile, about 1 kilometer, and it made it about out to here after 25 minutes, and that's when it died. And I noticed it suffered a minor structural failure here. I think this actually happened while I was towing it back, and it kind of bumped against the ramp at the end. So still only one motor is running. I'm gonna swap the connections from one motor to the other ESC, and that way I'll have an idea of whether the motor's the problem or the ESC is the problem. Just swapped the ESCs from one motor to the other, and now only the other motor is spinning. So that tells me that either this ESC is bad or it's not getting a good throttle signal for some reason. Now I've put the motors back to their original ESCs, and I've switched which one is connected to which throttle signal, and no effect. Still only one motor. So through process of elimination, I can tell that this ESC is bad. It's hard to say what led to the ESC dying, but that is one of the things that I would change about the electronics. These are ESCs for RC planes and cars and stuff, and I think they're a little better suited to using analog signals rather than feeding them with an Arduino. Not to mention that tends to cause a little bit of programming difficulty because of the timing with all the serial connections and whatnot. Otherwise, I'd also like to upgrade the microcontroller. I'm really on the brink of what this one's amount of memory can do. I'd like to add in a switch somewhere. I've just been unplugging and replugging this to restart it. That's the main power to everything. I'd also like to replace my soldered together proto board with a custom PCB. That'll definitely help solve this kind of rat's nest and probably make it a little bit more reliable too. The zip tie battery mount is a little janky, but it held up just fine, as did the hot glue in the drilled holes. These motors have worked out fairly well, apart from their lack of torque, but they survived being underwater, especially for how cheap they are. I'm fairly impressed. I do like how everything's mounted in here on Velcro tape. That makes it really easy to pull stuff for diagnostics and troubleshooting. I also might want to change out this RC receiver for like one of those Arduino RXTX serial communication radio modules. This thing uses a lot of analog pins, and it's a little bit annoying to deal with. Also a little better suited to analog RC stuff, not necessarily great for microcontrollers. I could definitely shorten this cable, but it is the GPS antenna, so I'm afraid if I cut it and reconnect it, my signal might not be as good. In conclusion, it worked. It successfully navigated itself towards a path of GPS coordinates up until an ESC died and suffered a hardware failure. But I do plan to repair that, as well as make all kinds of improvements to this, including an idea I have is to implement a sonar depth sensor that will collect depth data as it travels and make a 3-dimensional depth map of the pond it's traveling on. So I definitely plan to come back with part 2. Thank you for watching this video.